Good evening.
Fine, Somen. That last class we are starting with that redox reaction and that how the analytical chemistry is means redox reaction is applicable in case of analytical chemistry. And last class also that I told you what you mean by that oxidation as well as reduction. So how the oxidation is means related, and how can you detect that oxidation is happening in the particular reaction, or reduction is happening in that particular reaction, takes place in that reaction. So if increasing of that is oxidation number, so that means oxidation it takes place, and if a decrease in oxidation number, so reduction is takes place. So I explained that was loss of electron and gain of electron also. So today we'll go ahead how the things will be appear in this redox reaction. As you know that particularly redox reaction has a great application in case of industry. So if you think that your that is battery, what you're using battery, so that in that that a redox reaction happen in case of that battery. Means so one side will go for the oxidation, other side will be reduction. Then if will that is a rechargeable battery, so the condition will be that so if that is the galvanic cell contain 1.1 volt of that is current, and if will, the if that is the value of that if external circuit, if it is a rechargeable battery, it will provide the electric current from the external source. So what will happen if the value of that is that provided current from the external source is more than the 1.1 volt, then oxidation the which one will be the oxidation and which one reduction in initial stage, so that will be that is swapping to each other, means reduction will be oxidation and oxidation will be reduction. If the that is the cell voltage is 1.1 volt, and it will supply the same amount of the current from outside, means 1.1 volt from the outside, then what will happen? There will be no reaction, means the cell will not work. If the thing will happen that if it is less than 1.1 volt, if we supply that less than 1.1 volt from the outside external circuit, then what will happen? That as usual behavior of the circuit will be there. That original, which one will be the oxidation half, that will be remain as the oxidation half, and which one will the reduction half, that will remain as the reduction half. So this is the types of means oxidation and reduction behave on the basis of that how the reaction is conducted, what kind of electricity that voltage you are providing to that. So now the comes to the point. So redox reaction has two half reactions. I told you yesterday when I started. So a redox reaction is two half reactions. That means so one half is oxidation half, second half is reduction half. So you, within a compartment, two cells will be there, and having two electrodes will be there. One electrode will be that is oxidation half, which takes place oxidation, and another electrode will be which takes place that reduction half, and both will be packed in a particular container. So this is the means mechanical part of that particular battery system and all the things. You have seen the battery. So lots of types of batteries there: cadmium battery, nickel battery, lithium battery. So many types of batteries there. Everywhere there is a oxidation and reduction reaction is there. Means redox reaction is there. So due to the that redox reaction, they are able to the electron will flow from the oxidation to reduction, and current will flow from the reduction to oxidation. Anode to cathode, cathode to anode. That will be the that opposite of the flow of current is opposite to flow of electron. If electron will not flow, so current will not flow. Simple things is that. So for the electron flow, as you know that oxidation half provides the loss of electrons. Electron will flow from the oxidation half to reduction half, and the current will from the that reduction half to oxidation half, that anode to cathode and cathode to anode. This is the simple process that which happened in case of that your redox reaction or in battery, right? So if we come to the point, we'll see that a redox reaction has have two halves. So I told you oxidation half, reduction half, what I share with you. So one is written here Fe2 plus 2, Fe3 plus 1 electron, that is oxidation half. I told you that is loss of electron, means increase in oxidation state. So in case of left hand side, that reactant side, Fe2 plus has 2 is the oxidation state plus 2, and in the product side that Fe3 plus and plus 3 is the oxidation state. So reactant to product, the oxidation state increases, hence it is the oxidation half, right? Oxidation state increases. So in case of selenium 4 plus 1 electron, it gives rise to selenium 3 plus. So in the left reactant side, selenium originally lose that 4 electrons. When it accepts that 1 electron, now it becomes the 3 plus. So that's why the oxidation state of the reactant side is 4 and the product side is 3. So that means the oxidation number is decreases. So that means it is reduction. So that's why, see, that thing is that if we combine these two reactions, if will that particular reaction which is written in front of Fe2 plus gives rise to Fe3 plus 1 electron, and there C4 plus 1 electron gives rise to C3 plus. If we combine these two reactions, that arrow mark is there. So left hand side you have to write, combining you have to write both the that left hand side at one side and also both the right hand side in the one side. So product side is one side and reactant side is one side. So we can write down it Fe3 plus C4 plus 1 electron gives rise to Fe3 plus C3 plus gives plus 1 electron. In the both side, if you see after net reaction, this is what is called the net reaction. So if you see in the both side, that reactant side 1 electron is there and product side is 1 electron there. That means both side having 1 electron. So that means reaction is balanced. So this 1 electron is known as N, number of N, means number of free electron. If it is not equal, means suppose I like to say, if in the reactant side 2 electrons are there and in the product side 1 electron there, you have to balance the reaction. So before writing this net reaction, you have to balance the reaction. Hence, the thing is that you can get the, means both side electrons should be equal. Should be equal. When you are writing any reactions, redox reaction, both side electrons should be equal. Suppose let us take aluminum in the reactant side, there is 2 plus, and in product side there is 3 plus. So 1 electron there, and here the chlorine is, suppose in the reactant side is Cl minus, and that is Cl is there in the product side. So that will what will happen is 1 electron in case of chlorine, but 2 electrons in case of aluminum. So that's why you have to means that you have to multiply the things and to equal the number of electrons in both reactions. So then you have to write down the net reaction. Now the thing is that here in case of, if you write down this reaction Fe2 plus C4 plus gives rise to Fe3 plus C3 plus, and both side electrons are same. So that means net reaction is possible. So thing is that here Fe2 plus undergoes the oxidation. So due to whom? Due to the C4 plus. So C4 plus takes the initiative to release 1 electron from that Fe2 plus. Then now in the product side Fe3 plus becomes. So that's why C4 plus just known as the oxidizing agent. So Fe2 plus becomes Fe3 plus due to C4 plus. So Fe2 plus undergoes oxidation due to the C4 plus, hence C4 plus is known as the oxidizing agent. Simultaneously, C4 plus undergoes, that is reduction. So due to the Fe2 plus, hence Fe2 plus is then the reducing agent. So this is the thing that which is oxidizing agent, which is reducing agent, you can also calculate. Okay. Now the things that if you have to understand the things, whole things, then now. So the thing is that redox potential, it is the important one. Redox potential, what is the redox potential? So thing is that that is stability. Actually, that if we say, if we think, so you know that Fe2 plus is more stable or Fe3 plus is more stable. So if you understand the thing, Fe2 plus is less stable than Fe3 plus. So Fe3 plus is more stable than the Fe2 plus. Hence, always the atom try to be in the stable condition to making their energy down. Hence, what will happen? Fe2 plus is less stable than the Fe3 plus. That's why Fe2 plus lose an electron. So as I do have, what is the chemistry belongs to? Chemistry belongs to the stability form. I don't know what you understand about the stable form, but for me, the stable form is lowering down their own energy. If I have high potential, I can speak 2 hours. I can take 3 hours of classes by this high pitch of voice. So after 3 hours, so I will down. That is not my stable condition for the human being, but that is the stable condition for the chemical reactions. So that vibration is high in case of that less stable, and it is vibration is low in case of more stable. So that's why Fe2 plus is less stable compared to the Fe3 plus. That's why what will happen, always Fe2 plus is stable. Okay, ferrous oxide is a stable compound, that I don't say that it's unstable, but thing is that when it gets chance to be the Fe3 plus, so it try to change its that oxidation number. So that's why when Fe3 2 plus is there and a selenium 4 plus you will put into that reaction, then what will happen, iron will get oxidized due to the selenium 4 plus and becomes more stable than the Fe2 plus and becomes Fe3 plus. So that's why that is the redox potential. Potential means how can I achieve my goal. That is the main thing. So potential means, so iron is more stable in this case and less stable in this case. So that's why it gives the one electron and try to be more stable. That is the redox potential in this case. Okay. Now we'll come to the point. Significance of redox potential. See, significance of redox potential means potential is essential, and why the value, you have seen that this is the table half reaction and redox potential value is given. So as you go down in this table, so there is actually there is see, in below there is minus 4.41 up to minus 3.04. Okay, up to minus 0 sorry 3.04, 3.04, and in the top there is plus 2.65, that is fluorine. Okay, so if value is just a second please. Okay, so now the thing is that, so table says that in the fluorine in case of F2, the first line of this, and the electron potential value in volt, that is plus 2.65. Okay, now check it out. The value is decreases, plus 2.65, then plus 2.01, then plus 1.82. Like this, it is going to the value decrease, decrease, decrease. And in case of C, that 0 is case of hydrogen, right? So here 0, that is C, the hydrogen having the 0 value, right? And again increase, again decrease, 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 going to the lithium. So as you know that if value is more, if this potential value is more, that behaves as C. If it is okay, now see that in the above example, iron, we consider iron as the, what is that? Iron is the that reducing agent, right? Reducing agent. See that where is iron? Here is iron. Fe3 plus 2, Fe2 plus 0 plus point plus 0.77. If we go to the selenium, now check it out. Selenium. Selenium here is okay. So iron selenium is not okay. Let me check it out. Okay. In this case, selenium is not mentioned in this table. Okay, selenium is not there. So now the thing is that what happened here. So if value is in more, value is more. If potential value is more, that will be oxidizing agent. If potential value is less, that will be reducing agent. So now check it out. So fluorine is acts as an oxidizing agent, strong oxidizing agent, whereas lithium is known as the strong reducing agent, because value is decreases from the fluorine to lithium. So you have to understand. So which one, if two electrode are given in the reaction, That means copper is given and that platinum is given. Suppose the copper is given and platinum is given. Now check out copper. Copper here is plus 8 plus 0.86, and there that if you go to the nickel, if you go, nickel is minus 0.25. If two electrodes you have given, that copper and nickel, so now you think which one will be the oxidizing agent and which one which will take part in the oxidation and which take part in the reduction. So that is obviously copper has the more value 0.86, so that will be that take as the oxidation half and as the electrode, and nickel is will be used as the reducing electrode in the reduction half. So that means it will decided that whether it is prefix value or already measured value. So on the basis of that, you can also check it out. Now if you come down, now see that here is the now come to the electrochemical cell. Now electrochemical cell, what do you mean by electrochemical cell? The electrochemical cell, the cell which convert chemical energy to electrical energy. The cell which convert chemical energy to electrical energy, that cell is known as, that system is known as the electrochemical cell or electrochemical system. So that means you will use your chemicals, and you will get the electrical current. So that means here the flow of electron will be there, and yeah, Mr. Alexander, that thank you very much. Thank you very much. You got that. Let me check it out. See, 4 plus is given. Okay, fine. It's plus 1.44 is given. So plus 1.44 is given. So that means it helps. See that. Thank you very much. So I was unable to find out, and thank you for your help. So in that case, that iron is given. Iron undergoes oxidation as the selenium value is more than the that iron. So it is oxidizing, behave as the oxidizing agent. Thank you. So that's what I cleared also. So thing is that now the part is that electrochemical cell. So what do you mean by electrochemical cell? Electrochemical cell means, so it is convert electrical energy to it converts chemical energy to electrical energy. So that means first chemical reaction will be happened. Unless the chemical reaction is not started, so your electrical energy will not flow. So that means once that chemical reaction started, then there will be oxidation and reduction. So in oxidation, from oxidation to reduction half means anode to cathode, the electron will be flow, and the cathode to anode, the current will be flow. That what I told. So there is a salt bridge to make the electron balancing of that one. So now if you come to this particular picture, so now check it out. In the left hand side, your zinc sulfate, and zinc sulfate solution is there, and zinc electrode is used. In the right hand container, so that is copper sulfate solution is there, and copper electrode is used. And in the salt bridge, there is a that KCl solution with that is known as what is gelatin solution. So that is K plus and Cl minus will act. So Cl minus will attract, because as zinc electrode Zn SO4 is there. So Zn SO4 breaks down into Zn2 plus and SO4 minus. So then 2 minus. So Zn2 plus will attract the Cl minus, and also in that segment in the copper sulfate solution, Cu2 plus and SO4 2 minus. So Cu4 that SO4 2 minus will attract to the K plus. So that will be, actually the thing is that this is not simple things what is mentioned here. So there will be a charge imbalance will there. So if once that various charge will come, suppose that Zn2 plus that side chlorine will come, and the electrode will be supposed to covered by the chlorine ions, so minus ions. All Zn2 plus will attach with the Cl minus. Then how it is possible to pass the again Zn2 plus from that one? So that is a technical process. You will understand that mechanism later on. So this is the actually the electrochemical cell is otherwise known as Daniel cell or primary cell or Langlands cell. It is otherwise known as a Langlands cell. It is another terminology, Langlands cell. So this having two containers. One is oxidation half container, second is reduction half container. In oxidation half container, zinc sulfate solution is taken. Zinc electrode is used. In reduction cell, that is copper sulfate, which is known as cathode. So it is there. Okay, so that reaction will be there and connected with a salt bridge. Salt bridge is connected to the KCl plus HNO3 KNO3 solution. Okay, KNO3 solution is there. Okay, on the basis of that, reaction will be there. So now the come to the point. So calculation of EMF value. Nast equation. The scientist Nast has established an equation that is known as the Nast equation. So that particular this main motto of this reaction is to find out different variables like strength of the how much voltage EMF cell, E cell, EMF cell. What is E cell, EMF cell, inert cell, number of free electrons. You can calculate all the things. That concentration of the oxidation half, concentration of the reduction half. So Nast is having the produced one that equation. So E cell is equal to, that is EMN slash M likha hai. So that means this is the metal that oxidation half. So E cell is equal to inert cell minus RTNF ln oxidation, concentration of oxidation by concentration of reduction. Actually, this value of that is that RTN, R is real gas constant, T is equal to temperature in Kelvin, and F is equal to Faraday's. So these three things are constant, and ln will convert it as yesterday I told you. So ln and log, there is a relationship. So 1 ln is equal to 2.303 log. So we have to convert log into the ln. Hence, here ln means 2.303 log. Okay, so 2.303 log, R is the constant value, temperature is also constant because in Kelvin, and Faraday's constant is there. So if we put together all the value will be 0.0592. That means later on the equation will be converted in the E cell is equal to inert cell minus 0.0592 0.092 log oxidation half divided by reduction half. One more thing, right now I told you before some time. So if the equation is number of that electron is not equal in both the sides, so then what will happen? You have to balance it. So when if you multiplying any number with the oxidation half, so that means that the concentration of that particular oxidation half will provided to you, that value will be that power of that which you multiplied in the that to make the balance of that equation, that value will be square of that one or triple of that one, whatever the things. Okay, it will come down to the reduction half. If that particular thing is multiplied when you're balancing the equation, then what will happen? That will be the power of that particular reduction half. So that will be careful about this one when you are doing the solution of this particular type of examples. Okay, now the thing is that it will come to the point. So okay, that is not the issue. Now see, half reaction of this one. Let's write the Nast equation is there. E cell is equal to inert cell. Whatever the value you can find out. 0.0592 log concentration. Okay, so that is the thing. On the basis of that, you can put the value. Where is oxidation is going on? What is the reduction is going on? After that, you have to put the value of that and do the calculation. So ultimately, so I told you that the value is that means if altogether R is the constant, T is the constant, F is the constant, and ln will convert to the log into 0.303 log. So that means when you multiply it and calculate all the things, multiply and division will be numerical process will do. So you'll get out 0.0592. It's 9 is mentioned here divided by n. Okay, log then concentration about that. So you will, that is the formula. Okay. Then cell potential, exact that cell potential you can find out. Same thing is there here over, same thing. And reaction at the anode end, anode if we find out the anode side, so we'll put the value of anode also. If the put the value of cathode also, cathode side is there also. So you can do it accordingly. Okay. Anyone has question in this Nast equation or electrochemical cell?
No, sir.
Okay.
No, sir.
Okay, that's fine. So it actually you have learned this one, but only the simple things are there. You can go through that. Now come to the point, redox titration curves. So this is the as you know that you understood the redox reaction. So on the basis of that you have to find out the value. So here is the that means K value, we got the 7 into 10 to the 11 in the this above numerical process. So that is the question is given. So titration by Nernst equation, Fe2 plus C plus and all the things selenium is given there. So after the calculation all the things, log K is equal to 11.84 and K is equal to 7 into 10 to the 11. That is the value you have to calculate. Okay. So this is the value of what is this value will represent in the that is your titration curve. Okay. Suppose if you got the potential before starting the titration, okay, potential, okay, that's not issue. Let's go to the direct go to the curve. Okay, now come to this. So see that the above results of the calculation can be plotted as a titration curve as shown. Okay, so if you using, see, now the thing is that I just have enlarged my screen. Okay, now see that in the below there is volume of 0.1 m cerium, that is C plus, and 4 C4 plus and sulfate. Okay, and this is your E volts. So now the thing is that if excess Fe2 plus, as you know that we are doing the titration between iron 2 plus and C4 plus. Okay, cerium 4 plus and Fe2 plus, sorry, Fe2 plus and C4 plus. When doing a titration, so in initial stage when Fe2 plus is more excess, because you have taken that particular substance which having the Fe2 plus concentration is more. Okay, and you are titrating against the cerium C4 plus. So then what will happen, that will be time, the value will be decreased time to time. Fe2 plus value will be decreased and C4 plus value will be increased at the one point in 1.10 volt. At the 0.70 volt, the value of that Fe2 plus is more. But when it increase, when the titration is going on, means reaction is going on, so at 1.10 equivalence point, means Fe2 plus value and C4 plus value will be remain equal in that point. So after that, C4 plus value will be excess. That will be excess C4 plus, and Fe4 plus value will be less. So that means you have to understand when oxidation half is there, so volt of that one which is read means now the C that value of that E volt will be increases in case of Fe2 plus to C4 plus. So in C4 plus more, when the E volt is around that for 1.45. When the excess of Fe2 plus is there, the value is around that 0.69. So that is the plot against the means titration against the that oxidation and reduction. Okay, then redox indicators. So that means here the redox indicator is a compound which can undergo redox reaction and change color depending on the potential of the solution. So as you earlier know that indicator, what is the job of, what is the work of that indicator? So it is change the color. So when at a particular point, when the value increases, so that will be color will be changed. So that is the thing. The oxidized and reduced form of the indicator have different colors. So as you know that last class we have discussed that one in sometimes it is blue in acidic medium and in alkaline medium it is red. So like that, here the color will be changed in oxidation. When the oxidize, it is that color will be one, and when it reduce form, it will color will be changed. So color will be changed. Okay, so like that in oxidation it is mentioned that in oxidation indicator color is X. So when it lose electrons, so it will be, that will happen, it will go to the redox half. So reduction part. So then indicator color will be Y. The change in color will be placed over there, right? So intensity of color will be changed. So this is the fact. Okay, it will come down. That is same thing here. That is explained here over. Okay, which particular that is like your diphenylamine and that phenyl benzaldehyde and diphenyl benzaldehyde. So that is means it is usually diphenylamine is colorless in case. So when you treated with the any kind of things, it will colorless again. So again it will be changed in the when voltage that volt of it undergoes the reduction reaction, the violet color will be there. So that means color change will be there. So here some of the titration against the color, the standard titration reduction potential value, and the color of the oxidizing and reducing form of the some redox indicators. So if we say that methylene blue is there in the color of reduced form is colorless, but in the oxidized form it is blue, and the standard transition potential is 0.53. Okay, so that is 0.53 when that temperature means volt will be changed, so that after that color will be changed. Suppose so diphenylamine if you take that it is colorless in the reduced form, and in the oxidized form it is violet, and the standard potential value is 0.76. Like this you can check it out whether what is exactly happen, what is the color, and after that form what will happen. So this should be that you have to memorize all the things. So redox titration is non-aqueous solvents, in non-aqueous solvents. So that is what will happen here. So redox titration in non-aqueous media has wide scope for the determination of the compound which have the following characteristics. What are the following characteristics? The compound are insoluble in water. So non-aqueous solvent. If it is non-aqueous solvent, so the compounds are insoluble in water. And second, the compound react with water through hydrolysis or oxidation. The compound are decomposed by the medium or aqueous redox titration, that is acid-base reaction. So that's why if water will be present in any kind of redox reaction, then probability of that, so that reaction may happen. So that's why in non-aqueous solution, means without water, if you do the so many good performance you can do, okay, that calculation will be better more than the this situation. So criteria for the solvent selection. Okay, so what is the solvent selection criteria? The solvent should be resistant to the attack by the reagent. Okay, that solvent should not attack by the reagent. So before that, if the attack will be there, then will be reaction. Then your whatever the experiment you are doing, that will be go to the false medium. This permit reaction to be carried out over the wide range of potentials. If it will be attack, so that means then will be reaction will be happen. So many things will be happening inside that. So many reactions will occur. So what you want to find out that may not be get. This is so because some of the non-aqueous solvents may extend the range towards the reducing condition, while other may do so towards the oxidizing condition. So this is the scenario. For example, dimethyl formamide so can be used as a solvent for redox titration involving powerful reductant such as the chromium 2, but it is oxidized even by the mild oxidizing agents. So this is the scenario. Second, what is the criteria? The solvent should be capable of keeping reactants, and if possible, products are well in solution. The solvent should be capable of keeping reactants, so that means solvent reactants in the safe mode, in the because you have to do the titration against oxidation and reduction. So what solvent you are using, that should be in safe mode. So if possible, product as well in the solution also, that's product also. So as you know that electron transfer reaction tend to be slow unless appreciable portion of the reactant are present in the ionic form. So dielectric constant of the solvent must therefore be kept very high so as to minimize ion pairing that slows down the reaction rates. So that's why you have to, this is the mechanism. If electrical current will be more to make the faster reaction, so that then ions collision will be high, so then the rate of reaction may be high. So that's it. It is better to keep such kind of a reactor, what is solvent, to keep the reactant in safe mode, and also in product also the product. In addition to the above consideration, the solvent should be easy to handle. The solvent should be easy to handle. Let us take up the such issues related to each handling. Some solvent may have favorable resistance and dielectric characteristics, but are sometimes difficult to purify. So this is the main issue, a significant source of error, and hence such solvents are ignored. So many solvents are there which is favorable resistance but dielectric characteristics, but sometimes difficult to purify. Hence They cannot be, means error will be there. So that's why you have to ignore this kind of solvents. Some solvents tend to react with or absorb atmospheric components and need to protect it from the exposure of air. Example, acetonitrile and dimethyl formide. So take up the water even of the brief exposure of to atmosphere. So ethylene diamine tends to absorb carbon dioxide. So these are the things. Actually, this kind of a solvent you should be careful before the using. Like that, so many things are there. Many solvent like ammonia, sulfur dioxide, hydrogen sulfide, nitrosyl chloride, etc. have low boiling point and require low temperature condition. As a solvent working at a room temperature is an ideal choice. Such solvents with low boiling point also are not desirable. So low boiling point and low temperature, in this case, if it is working, so that means temperature is not also essential part of it. This kind of solvent should be avoided. Okay, some of the characteristics of a common non-aqueous solvent. Acetic acid. So characteristics of a common non-aqueous solvent means acetic acid, it has a low dielectric constant, as you know that. So acetic acid is a weak acid and it cannot release its hydrogen ion easily, because due to the presence of what is it? That a carboxylic acid group usually in the dimer condition present, and also OH hydrogen bonding is there. So it is dielectric constant is very low. It is difficult to purify and not convenient to handle. So acetic acid is not the useful, that is solvent, because what I told you, that is dielectric constant is there, constant is very low. As you know that there is dimer formation is there. So that a carboxylic acid group usually forms the dimers. COH group, like the oxalic acid, COH bond COH, that kind of things will be happen. So, and also that hydrogen bonding, intermolecular hydrogen bonding is there. So that's why it is very difficult to make it purify. That is why it fails to meet the criteria mentioned in the previous subsection. So that means acetic acid is not a good type of solvent. Okay, that acetonitrile, it is versatile solvent for a large number of interesting analytical electron transfer electrons. The reason for the popularity include a convenient liquid range, ready availability, a wide electrochemical range, moderate dielectric constant, and low toxicity. However, it has the disadvantage of being, it is oxy. Now, up till this, all the favorable conditions is there. Okay, now what is the disadvantage of being difficult to purify and has tendency to polymerize? Okay, polymerize means dimer formation, means one to another, they will means make the bond. So in the presence of the acid and base, it is powerful solvent for the wide range of organic compounds and a number of inorganic salts. Though its solvent's action is low polarizability, relatively poorly, with the resultant the many anionic metallic chlorides for the examples. So that's why this is has the so many things, but so many favorable things, but purification process is very difficult. As you know that is polymerize. As you told that dimer carboxylic acid, sorry, that acetic acid forms the being the having the carboxylic acid group, acetic acid has the form the dimer. So like that acetonitrile will form the polymers. So polymerize compounds. So not polymers, polymerized compounds, multiple that acetonitrile will tag each other. So that's why one relative stronger bond will form. So it is not suitable also. So dimethyl formamide. So it is a solvent that which only a few applications as an analytical redox solvent have been reported, but is of considerable promise. So that means it has very less number of use in case of your redox as the redox solvent. It has a dielectric constant close to that of acetonitrile, nitromethane, and dimethyl acetamide. It dissolves many organic and inorganic compounds, has a wide liquid range, and is thermally stable. Okay, so these are the conditions. So that's why may not be favorable. So like this, dimethyl sulfoxide is also that types of that is particular things, non-aqueous solvent. So then application of redox titration. This is an important area where you can use this one. So oxidimetric reagent. as the oxidimetric reagent potassium permanganate. So as you know that KMnO4 potassium permanganate is in acidic medium. It gives as the redox reaction. So because MnO4 will go MnO4 in this case. So in case of MnO4, so if you find out that +7 is the oxidation state in the above reaction, MnO4 minus plus 8H plus 5E gives rise to Mn2 plus 4H2O. In this case, MnO4 manganese having the +7 oxidation state, and the right hand side, in the product side, manganese has the +2 oxidation state. That means value is decreases and it is reducing in nature. Okay, it is reducing nature. In neutral medium, potassium permanganate is reduced to manganese dioxide. Okay, MnO2. Manganese dioxide again, it acts as an oxidizing agent. So these particular things behaves as the MnO2 is a good oxidizing agent. So in case of a Mn, that a Mn2 plus, when KMnO4 turns to the MnO2 and MnO2 again turns to the KMnO4, so that is both the oxidizing agent and a reducing agent it acts. So oxidimetric reagent is known as the oxidimetric reagent. Both it acts as both oxidizing and also, and another was KMnO4 says K2Cr2O7 potassium dichromate. When potassium dichromate will treated with here MnO4 KMnO4, so then it will give the MnO2. That means potassium dichromate and MnO4 acts as the here MnO4 acts as the reducing agent and KMnO4 undergoes the reduction. So that means CO2 will be formed. Like this, the diametric reaction is there, oxidizing reaction. So many things are there. Then if you come to the cerium IV, cerium IV 4 plus. Okay, cerium 4 plus sulfate is a powerful oxidizing agent in acidic medium. So if acidic medium means that your reaction should be conducted in the acidic medium. So in that C4 plus is a powerful oxidizing agent. What I told in the discuss in this case. So electron potential value of that SCl4 is 1.70 and 1.60 volt of HNO3 and 1.42 volt in H2SO4 solution. Ceric sulfate is a primary standard and the solution are remarkably stable. So that means this will be in the acidic medium. These acids if you use in acidic medium, so cerium 4 plus will act as a powerful oxidizing agent. Okay, then potassium dichromate. Just a second, please. Okay, now the thing is that if you come down, so potassium dichromate also, I told you about the potassium dichromate. So potassium bromate, so KBrO3. So this is a potassium bromate. As you know that it is a powerful oxidizing agent in acidic medium. Okay, so electron potential value is 1.44 volt. So that acidic medium means acid should be there. So it will be the potassium bromate is a primary standard as the reagent can be obtained in the pure state. Its standard solution can be prepared with a direct Wesing. So that is the process you can go through this one. Then potassium iodate. So KiO3. So it is actually this is the oxidizing agent, strong oxidizing agent which can oxidize the thing. Just a second, please. Okay, now we'll come to the point. Iodine. So iodine actually all the iodine is a strong oxidizing agent. So as you know that also the halogen group that fluorine, chlorine, bromine, iodine all are the oxidizing powerful oxidizing agents. So that I2 or iodine couple is medium of oxidizing power, whereas the iodine is a weak oxidant compared to the down the group will come down. So oxidizing power will be decreases. Iodine is a relatively weak reductant also. So it is relatively also weak reductant. So as you come to the down, so of strong oxidized to weak oxidizing agent. So fluorine, chlorine, bromine, iodine. So on the basis of that, iodine is a weak oxidizing agent, and what it has more oxidizing power is there also. on the basis of that one. So reductometric reagent, dimetric, so that is oximetric reagent and a reductometric reagent. Iron. So iron is weak reductant. I2 plus is slowly oxidized by air in sulfuric solution and find the common use. So Fe3 plus 1 electron gives the Fe2 plus. So this is a weak oxidized, weak reducing agent. Chromium 2 plus and a titanium 3 plus. So these two are very powerful reducing agent, but they are readily oxidized by air and consequently are difficult to handle. The reduction equation and the potential standard potential are as follows. Okay, you can read this one. Cr3 plus 1 electron gives Cr2 plus. Electron potential value is minus 0.41 volt. Titanium 2 plus, titanium oxide 2 plus gives rise to titanium 3 plus, means 2 plus to 3 plus. So it is 0.04 volt. Then these are the things which is associated with this the chapter redox, that is chapter, and we have finished this one. If you have any questions, you can ask me. Anyone has any questions? If you have any questions, you can ask me.
No, sir.
Okay, that's good. Just a second. I'm coming to another another unit. Just a second.
So I have just recently taken part in this
Yes.
class.
Sorry.
So I have just recently taken part in this class 10 minutes ago. Can I get the earlier recordings of lectures?
Actually, that it's who is may I know your name, please?
Raman Kumar, sir.
Okay, sir. So then that today's class or early class?
So today I have just joined it 20 minutes ago.
Okay, no problem, no problem. We'll actually that yesterday that class details and today's class details will be so first unit class you have gone through that your mail you have got.
Yeah, I got through mail only, sir.
Okay, that's we'll send through the mail. Okay,
sir.
We'll send. You will get all the things over the mail, right, over your mail. So that is the best option because details will be supplied from the IGNO side.
Thank you, sir. Thank you.
Okay, thank you. I'll provide to the IGNO and IGNO will directly send to your mail ID. Right? Don't worry.
Right.
Okay. So just be there. So I'll coming to another that portion. This one. Just be there. Yes, Alexander. That is Alexander. That is iodine has both capabilities of oxidizing and as well as reducing agent. So that is your question, however. But iodine is that is weak. That is see that it depends upon the situation. It will behave like oxidizing agent as well as reducing agent. Both are there. So group 17 members usually use for the that, as you know, that fluorine is used good oxidizing agent rather than the reducing agent. So but the behavior will be changes. See, water people say, yeah, I'll tell you. You know that that water, if we say, you'll understand. I will take the water. Water has you understand that water is neutral. Which water we are drinking, that is neutral in nature, but it has also acidic nature. It has also basic nature. So it is actually, don't be confused. Every that particular compound or element, it has some that oxidizing nature, some reducing nature. It depends upon the compound. Suppose if I'll take water, how the water behavior will be changed. If I'll take one acid, If I take a strong acid like hydrochloric acid and I'll add the water, then what will happen? Then a hydronium ion will be there. Means here the water behaves as what? That behaves as your base. But if I take a weak acid and I'll use that particular, suppose that that amount, that if I use the water and we along with some that base, more base, strong base, and in aqueous medium, so that what will happen? The lone pair which is present on oxygen, that will donate to that particular things. So that will, it will behave as the that Lewis acid. So thing is that on the basis of that one, so we see it will come to the that is your halogen. So halogen is a fluorine is the smallest in size, okay, and high electronegativity in nature. It will come to the that group 17 member. So fluorine is a that is that down the group, that atomic size increases and electronegativity value decreases of a halogen group 17 members. So that means fluorine is that is smaller in size. Also in the whole that is whole total periodic table, if you calculation, fluorine is the smallest one, and it has the that if you do not compare with the hydrogen. So fluorine is the lowest smallest size, has smallest size, as well as high electronegativity value. So high electronegativity value means what? High electronegativity, it will accept electron, it will not donate electron. High electronegativity means pull the electron towards itself, electron affinity. I don't want to release my electron. So because that is your radius, atomic radius is very small in case of fluorine. So screening effect works very less. So that's why the nuclear force, effective nuclear force is more. So that means fluorine has 7 free electrons. Fluorine has 7 free electrons on its outer orbital. It can donate 7 electrons, no problem. But it is not able to donate the electron because of size. Yes, that's iodine. See that will come to the point. Iodine has the highest electrode potential value and thus the weakest oxidizing agent, the strongest. That is okay. Electrode, from where the electrode potential value will come? Electrode potential value is, that is okay. That is we express these things for our better work, but we have to understand how it happens. If you come down the in the group 17, iodine is larger size. So if larger size, what will happen? Larger size means it will donate its electron, which because atomic radius is more, it's a larger, so it is easily donate its electron. If electron donation and electron acceptance depending upon that, you know that. So I told you, oxidizing, what is the work of that one? So it will be that acts as the strongest oxidizing agent. So weakest oxidizing agent and the strongest reducing agent, because of this nature, iodine donate its electron and change into the different that color will be changed. So that's why it depends upon the electrode potential value. So electron potential value is reflect on this by that on the calculation point of view, but you have to understand what is the atomic structure of that one. So that's why that is the main issue. Okay, now come to the next, that is as we going through the titration. So next, precipitation titrations. So precipitation titrations is the thing that how the precipitation titrations will be occur. So if we redox titration and complex metric titration, if we go through that one, there is so many things are there. So we shall discuss titration curves in details. So then we'll discuss Morse, Fazan's and Vollard's titrations, followed by the application and precipitation. So this Morse titration, Fazan rules and Fazan titration is there, Vollard titration is there. So all these 3 titrations are most important. And what is the objective of this one? The objective of this one is to find out precipitation titration, is to find out, understand the principle of a precipitation titration. What is the precipitation titration? You have to understand. This is a new word perhaps for you. Calculate and plot a precipitation titration curve in which a single precipitate is formed. So single precipitate will be formed in this reaction. So determine the graphic endpoint of a precipitation titration curve. You have to determine the graphic endpoint of the precipitation titration curve. Then explain precipitation titration curve in which two precipitants with much different solubilities are formed. Next, explain how formation of the colored precipitate can be used to determine the point. So these are the things we have to go through. So precipitation, titration, and introduction. Okay, leave it. This the okay. Let us to discuss this one. A precipitation titration is one in which the titrant form a precipitate with the analyte. So precipitation will be formed in this reaction. Although it might appear that numerous precipitation reactions could be made the basis of a titration, requirement must be met that seriously limit the number. The basic requirement are that the reaction must be sufficiently rapid and complete. Means that it should be faster. Means that what are the circumstances you have to use, what are the periphery, what is the electrical equipments you will use, that should be working properly. And the basic requirement are that the reaction must be sufficiently rapid and complete. Let exist to locate the endpoint. Some difficulties in the meeting these requirements must be noted. Precipitation frequently proceeds slowly and starts after some time. As you know that precipitation immediately will not form. It will after few seconds or 1 minute of time precipitation will start, or 2 minutes of time. So many precipitates show a tendency to absorb and thereby uh, co-precipitate the species being titrated or titrants. The indicator may also be absorbed on the precipitated form in the three precipitates in the highly colored. So visual detection of the color change at the endpoint may be impossible, but even where the white precipitate is formed, the milky solution may be still make location at the point of difficult. Okay, so that means you can observe different on the basis of that. If it is milky or any color may be difficult, but it will be we have to observe that one. So feasibility of the precipitation titration. Okay, feasibility is not essential. Okay, titration curves. A precipitation titration curve has the same general shape as that of the strong acid titrated with a strong base. So we have discussed strong acid with a strong base. So it is similar. Precipitate titration curve has the same general shape, the basis of that strong acid and strong base. In the case where the precipitate has very low solubility, it is shaped like the curve for the titration of weak acid with a strong base. So these two things are there: strong acid with a strong base initially, and after that it will be weak acid and a strong base when a more soluble precipitate is formed. Okay, as an example of the former, consider the titration of the 100 ml of 0.01 molarity potassium iodide with the 0.1110 m silver nitrate titrant the reaction. Okay, so what will happen here? Ag plus I minus gives rise to AgI, silver iodide. Okay, and the AgI product as a relatively low solubility product, means precipitation will be there on the below. So a concentration of KSP is equal to concentration of Ag plus and the concentration of I minus is equal to 1.0 in 10 to the minus 16. This is the calculation value. On the basis of that, what is the concentration is given. In 100 ml of 0.01 100 m molarity, I minus there is initially 100 ml into 0.01 0.000 millimole per ml. So that means 1.000 millimole of I minus is present. So this is the titration fact. We have got it out, and if you go to the curve, so that means curve will be represented like this. Come down. Okay, like this. So the curve is this. So plot a precipitation titration curve. The titration curve of the titration of 100 ml of 0.0100 molarity Ki with the 0.1 000 molarity of AgNO3. If you titrate this plot, so here the plot is there. See that this side is just a second, please. Just a second. I have a phone call. Hello. Yes, my mic was off because that I have some an important call. So if we go to this, so here silver nitrate is there below bottom part, and the in the here is AgI is there, and the core will like this. Okay, so core will be like this. The here is the potential of iodine. This side it is the potential of what is the silver is there. So you have to calculate on the basis of this. You just go through this one, read for some time. Okay, go through this particular noting, and there is core analysis. The core, I am giving the 2 minutes of time. So after that we'll come to the discussion. So check it out, the core. Check it out, the core, and all the read the things facts, and I'll come. I'll online. These are the curves. What is that you have to observe these curves, and you have to do like that. Now the point is that what are the factors affecting the sharpness and of endpoint? Both the magnitude and the sharpness of the endpoint big influence how the equivalence point can be estimated. So both things, that magnitude, the sharpness of endpoint. Therefore, it is important for us to examine the variable that can influence the shape of the titration curves. So that it is essential. The properties of the indicator also affect how well equivalence point can be estimated. So now the thing is that, so it is better that you have to judge all the things like magnitude and sharpness of endpoint. Okay, the silver ion concentration before the equal valence. Okay, the silver ion concentration before the equivalence point depends partly on the original concentration of bromide ions. That above reaction is there in the bromine and silver. Okay, so ion is there, while after the equivalence point it depends partly on its own original concentration. As a result, high concentrated of analyte and the titrant product produce larger and sharper endpoint break than do low concentration. So these are the facts, which is factors affecting the sharpness and endpoints. So be careful about this. Then completeness of the reaction. The equilibrium constant for the reaction in which the precipitate is formed usually is just the reciprocal of the solubility product constant for the precipitate. So, for example, when silver nitrate is titrated against the potassium thiocyanate, the net reaction, net ionic reaction is Ag plus SCN minus AgSCN. So for which the equilibrium constant is K equilibrium constant is 1 by Sp 1 by Sp Ksp. So these are the plot against these particular things. Now exactly that what is the indicators for the precipitate titration. This is an important area for the precipitation titration. The titration curves thus described so as a rise in titrant concentration accompanied by the abrupt fall in analyte concentration of the equivalence point. Obviously, a reagent that responds to the abrupt rise of the analyte concentration at the equivalence point can be employed as an indicator. So the endpoint or several methods has been developed for the showing the endpoint in the precipitation titration. The better known of these have been developed for the titration involving Ag plus. They are based on the formula of the colored precipitate, turbidity, formation of a color complex ion, and absorption of a dyes onto charged precipitant particles. These methods are described in the following sections. So as we have discussed the Bullard Fazan and the Morse titration method is the important. So the Bullard method is that this is important area for your semester. In the Bullard method, chloride are fast precipitated with the excess silver nitrate. So Bullard method, in the Bullard method, that chlorine or chloride is fast precipitated with excess silver nitrate. Then excess silver is titrated with potassium or potassium thiocyanate. So what will happen? The formation of the color complex ion is FeSCN2 plus may be used to indicate that the end point when Ag plus is titrated with SCN, the titration reaction is Ag plus SCN minus gives the AgSCN. When ferric is present in the solution in the following reaction occurs at the end point, Fe3 plus SCN minus gives the FeSCN2 plus, the red complex ion will be formed. Means this is the Bullard method where the chloride is titrated against the silver nitrate and then followed the excess silver is titrated to the potassium thiocyanate. So these are the reaction based, and ultimately at the end of the point, so FeSCN2 plus will be formed, which is red complex ion. Okay, this is the precipitate is the form. The end point is readily observed by the intense color. As the color is red, so intense color is formed of SCN2 plus complex ion. In order of this means the indicating end point to work, the complex ion must form at the nearly equivalence point concentration of the titrants. When you do the titration on the basis of the Bullard method, so chloride and silver nitrate, when this will be formed, that the FeSCN2 plus ion will be formed, the red complex will form. That means your endpoint you have reached at the endpoint. The formation of FeSCN2 plus forms on the basis of the Bullard method. So this is what you say the Bullard method. The Bullard titration can of course be used for the determination of Ag plus by titration with SCN. So that means if you want to find out that determination of silver plus ion, so that means silver nitrate will be titrated against that potassium thiocyanate. So then what will happen? It can also be employed for the determination of bromine Br minus and I minus by adding an excess of the standard Ag plus and back titrating with the SCN minus. The determination of Cl minus by this process is more difficult because AgCl is more soluble than AgSCN and the reaction. So this is the Bullard method. You have to understand what is the Bullard method, what exactly use, what color is formed, which complex color will be formed, where is the restriction, what you can calculate, which one can you titrate it, what ion you can find out, or what concentration you can find out. These are all explained by the Bullard method. So you have to observe this Bullard method also. Then Bullard titration equilibrium is you have to go through this one. It's a mathematical area. Okay, then it is Fazan's method. So the Fazan's method is that it is another method. So these three methods, what is Moore's method, Fazan method, and Vollard method, all three methods are important for your semester. So be careful. The Fazan methods is a direct titration of chloride with silver ions. So that means in this method, in the same thing in the Vollard method, Vollard titration, this is chloride can be titrated against the silver nitrate, but here the chloride directly with silver ion from silver nitrate using dichlorofluorescence is an indicator. So Ag plus Cl minus gives AgCl, and the Ksp value is 1.8 into the -10. How the adsorption indicator works? So here adsorption indicator are dyes that adsorb or desorb from the surface of the precipitate near the equivalence point of precipitation titration to be useful for the end point indication. This must result in a distinct change in color either on the surface of the precipitate or in the dye of the dye in which it is suspended. So it is be careful. So two things, your color change in color you can find on the surface or dye where it is suspended, right? These two things are there in the important point, because sometimes people only check the surface area and the color is not formed. So you can be you have to check to the dye surface which is suspended. So that is also possible, the color will be changed. So both the things should be important. If you check one, another thing you will not change, maybe some issues will be there. So here that AgCl dot Ag plus will be greenish yellow, whereas fluorescent ion will be pink in color. So that means change in color will be observed, and that means you are reaching over the equilibrium point. That means this is what you say the Fazan's indicator or titration. Then we will come to the Moore's titration. So Moore titration means you know that here the formation of a second color precipitate at the end point can be used for the determination of the end point. The second precipitation should have a solubility slightly greater than that of the precipitate formed in the by the reaction of the analyte and titrant. So brick red silver chromate. So Ag2CrO4. This is the brick red silver chromate compound. So Ag2Cr4, this color of this one brick red, meets the criteria for the second precipitate to show the end point of the titration Cl minus and AgNO3. These three reactions when you are reading, so that things is that chloride against AgNO3. So three things will be applied on the basis of, but color will be different in different substances. That will be changed on the basis of that titration. So you can observe this one also. You can go through this. Okay, now the indicator blank in the Moore's chloride titration. Compensation may be made for the Moore's chloride titration error by running, you know that blank. I told you the blank. Okay, that blank is a process of error. So the Moore chloride titration error by running an indicator blank. So you have to use here indicator blank. So blank commonly used to correct the determinant endpoint errors. So in the error and types of errors, we have a blank. How to use the blank? So that is also standard solution is there. Also, this is the use of blank. The perfect example of a use of blank. So you can use that blank point here. You have to read. You have to check it out. This one. So what will happen? A suspension of solid white chloride free calcium carbonate is made up in a solution having about the same volume of a titrated solution at the equivalence point, and the containing the equivalence point concentration CrO4 2 minus. The Ag plus reagent is added to the suspension until the end point color is observed. The volume of Ag plus reagent required to match the end point color is subtracted from the end point volume of the measure in the titration of a chloride. So this is the use of a blank here. So blank is used means suspension of a solid white chloride free calcium carbonate. This is the blank you have to use, and on the basis of that you have to calculate. So this is the perfect example of a use of a blank. Okay. Now the applications. So where you have to use this application, you will do the application estimation based on the precipitation and gravimetry. So on the gravimetry and the precipitation application, you have to use these three, that is Fazan's rules, Fazan's titration, your Moore's titration, and your that is Fazan's Moore's. Another is there. I forgot that. Is that? Volard. Okay, Volard, Fajans, and that is this Morse titration. You can use in different application it has. So application means estimation based on the precipitation and gravimetric. In this case, you can use these three particular types of titrations. So here substance determined as ASO4 3 minus, Br minus, I minus, CNO minus, SCN minus. Then endpoint will be Volard. Remark, removal of silver salt not required. Okay. So CO3 2 minus, CrO4 2 minus, Cn minus, Cl minus, C2O4 2 minus, PO4 3 minus, S2 minus, NCN2 minus, Volard is applicable. So BH4 minus modified Volard is applicable. Titration against Ag following by the this. Epoxide attack is epoxide two attacks are there. So this epoxide Volard is also, so K plus modified Volard is there. If it is Br minus and Cl minus, Morse is there. Also in Volard you can see you can use for the Volard, you can use Volard for the Br minus and Cl minus. But Br minus Cl minus, Morse is there. Br minus Cl minus, I minus, SCO3 2 minus, adsorption indicators you should use. VO4OH plus fatty acids, that mercaptans and electroanalytical methods you can use. Zn2 plus modified Volard, F minus modified Volard you can use. So these are the methods you can use in different kinds of things. What substance you have to determine. On the basis of that, you have to use this particular agronometric precipitation methods. So these are the things what I will cover in this chapter, that is titration and all the things. So if you have any questions, you can ask me. Okay. So Now this unit is that is, so this unit is completed. So let's go to the another unit. Just wait, please. Okay. So now the thing is that let's find the what are the types of instrument you are using in case of analytical that is just a second. So this is the instrument of to analytical sorry, introduction to analytical instrument. What type of instrument you are using in case of analytical chemistry? You have to understand that thing. Okay. So if you go to that particular see that all the instrument you have to understand. So if optical method is there, physical and chemical properties optical method is there. So absorption of radiation, photometry and spectrometry, spectrophotometry and atomic absorption, these are analytical techniques you have to use. Okay. So this means this is very clearly I'm going to tell you, if this kind of things are there, what type of technique you have to use. On the basis of technique you have to check the your instrument. So absorption of radiation, if they are photometry, spectrophotometry and atomic absorption, these three techniques you have to use. If emission of a okay, if emission is there, emission of radiation is there, then flame photometry, that emission spectroscopy and fluorescence, these three techniques you have to use. We have already read all the things. Scattering of radiation is there, so turbidimetry and nephelometry is there. So diffraction of radiation is there, X-ray diffraction and electron diffraction. Okay, now the come to the electrochemical method is there. So that means measurement of potential of electrode or change in potential, then potentiometry you have to use techniques. So measurement of mass of substance deposited on electrode, if we have that particular that area, so that means electrogravimetry you have to use that techniques. So change of conductivity is there, so that is also electrogravimetry you have to use. Measurement of the conductivity or change in conductivity of the solution is there, so conductometry you have to use. Change in diffusion current with the respect to the potential is there, so voltammetry and polarography you have to use. Then mass change of determination, mass spectrometry you have to use. Then radioactivity measurement is there, radio analytical method you have to use. So all these methods, techniques we have to, but you have to understand these things, where which principle you use in which techniques. So that means that is the most important thing. Okay. Then analytical balance. So calorimeter, photometer, and spectrophotometer. So calorimeter, as you know, that already we have discussed about that. So photometer is that. Photometer we have not discussed. Let us see the photometer. Then came to the development of photometer, in which the eye was replaced by the photoelectric cell. Okay, so that means photoelectric cell is used here, which produce a current, the intensity of which give a measure of the light falling on the photocell. This measures the light absorption by the solution concerned. Basically, this instrument consists of light source, a suitable light filter to obtain the approximately monochromatic light, a glass cell to hold the solution of the measurement. So photoelectric cell and a measuring device to record the response of the photoelectric cell. So these are the photometry techniques and all the things. Okay. If you come down, you'll see the spectrophotometer, spectrometry. You have gone through that one. So spectrophotometry you can understand also. So infrared spectrophotometer. So infrared spectrophotometry came into the field of analytical method much later. Although William Herschel in 1800 had reported that radiation existed beyond the red region of the solar spectrum, which heated up of substances. Unfortunately, he was not aware of that this absorption could reveal the modular structure of the substance. It was left by the Williams W. Covey's, who collected and first had published, okay, the IR spectra of nearly 131 substances. So these are the infrared spectrophotometry, how the developed is there, how it is happens. Then plane photometer, you have to go through this one, plane photometer and all the things. So then spectrography. So spectrography, the method, this is a spectrography, and the types of atomizer and atomization temperature. So that plane is around temperature 1700 to 3100 degrees Celsius. So electric arc 4000 to 5000, electric spark 40,000, inductively coupled plasma 4000 to 6000, then direct current plasma 4000 to 6000, glow discharge plasma, that is 400 to 600. These are the spectrophotometer. It will come inductively coupled plasma. So this will be a 6000 to 10,000 degrees Celsius atomic absorption. So is there. This is the process that we have already discussed. Then electroanalytical method, that is the oxidation and reduction reaction. Already we have discussed this one. So then role of a computer in analytical instrumentation. So computer is the fastest way to set up all the things, like your recording of that is screen recording, monitoring, and suppose how much amount of a chemical you have to drop, it's 1 ml, 2 ml, 3 ml, whatever may be, that only the programming system will there, and you will set the things, and on the basis of that you have to do the experiment, as I have already told you earlier. Okay. Then this is the area, and the terminal questions will come. What are the different ion sensitivity electrodes? That is, what are the general use of a flame photometer? You have to go through that one. What are the advantages of a plasma source? So these are the things. Self-acceptance Nessler tube is there. Nessler Unicap SP 300 ml to 14,000 high Higler biochem. So wavelength, reflector. So these are the things. It may be that come in the questions. You have to discuss in that. Okay, next. Just a second. Okay, now the thing is that next part of this one, the kinetic method of analysis. So as you know that this particular area that is associated with the kinetic method. So kinetic method means movement of molecules. Okay. So when the movement of molecules will be there, the collision will be there, and the reaction rate will be increases. Whether it is slow or it is fast, that does not matter. So we have to understand the things. Okay. So thing is that, so this is the kinetic method of analysis. Modern analytical chemistry make use of a number of methods for analysis based on chemical, physical, and physicochemical changes that are exhibited by the substance on the chemical reactions. So earlier in the first class, we understand that the three types of means that is chemical, physical, and physicochemical methods. So modern chemistries, that is scientists are doing such kind of things on the basis of that, procedures. So kinetic method of analysis is one such important method of analysis, and it is most commonly used nowadays. Every chemical process, whatever it name, nature, takes place at in a finite rate tending to on the equilibrium. I told you. So every chemical reaction having one that is rate, speed, and it will move towards the equilibrium condition. So on the basis of that, we have to calculate what type of it is, whether it is a reversible reaction or irreversible reaction, spontaneous, non-spontaneous, what is the speed, how the amounts will be deposited, within what time, what amount deposited at the equilibrium point, what within within a period of a time, what amount is deposited. So that's on the basis of that we can calculate a huge mass of compounds when from that will sample will collected and will do the reactions. Okay, some reactions are so fast and attain the equilibrium practically instantaneously. Some of them are slow and take very long time to attend the reaction. So if we go to the roasting of iron, it is very slow reaction, and it will take to reach the equilibrium point, it will take much more times, months, years of times. If we go to the blasting of a cracker, so it is the fastest reaction. We cannot calculate that. If will fire in the case of petrol, in if will communicate fire in the case with petrol, so it is very fast reaction, so the speed is very high. So but the thing is that the moderate reaction is most important. So the things that there are certain reactions moderate in nature and amenable to follow the course of reaction with suitable analytical techniques. So that means we are not able to calculate where if it is faster reaction means that is very fast reaction, we are unable to calculate the what is the amount will be generated. If it is very slow, we also unable to calculate the things. So only that moderate reactions can be calculated. Only the moderate reactions can be calculated. So thing is that that rate of reaction only the influence the moderate reactions. Fast reaction and very slow reaction we cannot calculate. We don't have much more time to wait for that one. It is maybe 1 month, 2 months, 3 months, 1 year. So means very slow reaction, like rusting of iron. If we'll say that it is that what is that fastest reaction, that is instantaneous time within suddenly. If we blasting of any cracker or firing in case of gas or petrol, so that is very fast reaction. That my motto is to say that we have to calculate this reaction on the basis of that what is moderate reaction, means it will the stipulated time. And suppose that if you say that what is the chemical kinetics of how it will measure. So we will travel from one position to another position A to position B, and it is 60 kilometer away, and you are driving your car or bike. So the speed is not uniform. So for 10 kilometers, my speed is 20 kilometer per hour. Then stoppage is your traffic is there, so your speed will be zero. Then some open space will be there. Your speed will be 60 kilometer per hour. So on the basis of that, average will be calculated, and on the basis we can access the things. So moderate reaction is essential for this one. For that, chemical kinetics can be applicable for the moderate reactions. Okay, it will come to the point that these are certain reactions moderate in nature and amenable to the follow the course of reaction with the suitable analytical techniques. Fast reaction technique are available for studying the very fast reactions. Okay, the very fast reactions, it's a nano and picoseconds. The most commonly used basic analytical techniques such as precipitations, acid base neutralization reactions, redox reactions, complementary reactions are equilibrium based on kinetic method, which some distinguishable trends in this unit will studying the chemical kinetics of moderate reactions. So in this unit we'll study the kinetic of moderate reactions in the dynamic region before the tends to attend the chemical reaction. So our target is to study about the moderate reaction, not about the fastest reaction, not about the slowest, so means very slow reaction. It is not possible to calculate in case of chemical kinetics. Okay, now the thing is that what is the objective of this one? So objective of this particular study is to understand the various methods of a classification and types of kinetic reactions. Second, utilize the different method of kinetic measurements based on the type of the reactions. Third is understand how the fast reaction are studied. Fourth is make use of the rate laws for the kinetic studies. Okay, so fifth is understand how to determine the catalyst, enzyme and substrate by the kinetic methods. As you know that, see that people say that catalyst as there is actually the some reactions are there. Fastest reaction we have to make it slow, that is poison. You can say it is poison. Okay, if it is fastest we have to make it slow. If the reaction rate is faster we have to make it slow, that is poison. If rate of reaction is very slow we have to increase that one, so it is that promoter. So on the basis of that we have to use so many things, that it may be the what is that your catalyst, enzyme or substrate by kinetic method. Understand the basis of the kinetic measurement and the types of instrumentation used. Okay, what type of what type of kinetic measurement you have to use and the instrumentation you have to employ it, so that you have to understand in these particular things. So visualize the application of kinetic studies to organic and inorganic species in the various areas, study of the make use of them. So this is the also the objective of the how that while we are studying this particular unit. Now that we'll go to the types of kinetic methods. Okay, this is important. So actually this is a practically useful chapter. As you know that you are having that practical chapter, this analytical chemistry. Everywhere there is some practical applications, so you should be careful about the practical applications. So now the thing is that if you come to the point, the kinetic methods are classified by the number of criteria. Broadly, it can be classified as the catalytic or and non-catalytic method. The catalytic method are further divided according to the type of reactions involved. Okay, if we come to the catalytic method, so that is non-enzymatic, that is homogeneous. Types of reaction is modified effects. So redox, the redox reaction is there, and chemical complex reaction will be there. Activation, inhibition, catalytic titration should be there. So then is catalytic method is enzymatic. So homogeneous, heterogeneous and modified effects you have to see that activation of activation and inhibition. So next is electrochemical method. So this is applicable for the heterogeneous type of compounds. Non-catalytic methods, determination of a single species, determination of mixture, different kinetics. Okay. So now the thing is that classification of experimental approaches for the kinetic measurement. Just a second, please. Okay. Okay. Now, the classification of experimental approaches for kinetic measurements. Mixing method. So that is mixing method means we will come across the batch mixing method, stopped flow mixing method, then continuous flow mixing methods, then relaxation methods, jump techniques, periodic relaxation techniques, and spectral relaxation techniques. Equilibrium method. So that is resonance techniques. Then we'll come to the that these are the areas you have to focus on, the that is types of kinetic methods. That by using this type of kinetic methods we have to determine so many things. Okay, so how the question is how can the kinetic methods are can be classified broadly. So if this is the broadly classification is there. So classification 1 is there, classification table 1 is there, general classification of kinetic methods. So then classification experimental and approaches to kinetic measurements. So on the basis of that you have to do. Now the measurement of reaction rates. This is the actually real that kinetic energy field. So how we will measure uh, particular reaction rate. So let us consider one that a reactant to product. It is a decomposition from the that one a product A, sorry, reactant A given the product P. The rate of disappearance of analyte and the C. Then when that A, particularly you will take reactant A. Okay, so two reactants are there, A and B, gives rise to product C and D. Let's have that A plus B gives rise to C and D. So initially when the reaction is not started, both the concentration of a reactant is A and the concentration of a reactant is B, both are 100%. So because the reaction has not started yet. So after some time, means when the reaction started, so concentration and the product will be formed. So concentration of A will decrease, concentration of B also decrease, then concentration of C initial stage, concentration of A was 100%, concentration of B was 100%, but concentration of C was 0, concentration of D is 0 also. So when the reaction started, concentration of that is A will decrease, concentration of B will decrease, concentration of C will 0 to increase, then concentration of D will 0 to increase. How much it is increase? How much amount of A decreases, that much amount, or a B decreases, how much moles? B A decreases and B decreases. Suppose X amount of A decreases, so and X amount product is formed, means C is formed. So that means X amount of A will be decreases, X amount of B will be decreases. That we have to understand. So rate of disappearance, okay. Rate of appearance and rate of disappearance means product. Rate of disappearance means reactant. Always reactant indicated to disappearance and that product always indicated to the appearance. So be careful about that. Terminology is there, appearance and disappearance. Okay. Now if you come to the point, so here the initially see that this graph is telling something. Okay. So this graph, go to the graph. This diagram. Now, initially the A is the reactant here, P is the product here. So A is the 100% is the top corner of left hand side, top corner. A was 100% means, and in the bottom that left hand side corner, the P is the 0 because the reaction is not started. So when reaction will started, after some time, A will decreases and P will increases. So at a point, they're both A and P both will be equal. That is called what you call the equilibrium region. So after that, when the equilibrium cross, so P will be go ahead and A will be come down. If in at the equilibrium use any kind, that chances of alternate of a reaction will be there. So if we'll see, if I'll tell some one example in the physical that concept point of view, if we'll stand on the 11th floor of a building, and it will have thread and a tied stone, the below one part of the thread and another part you hold, and whole thread you have to throw from the 11th floor to ground floor. So what will happen? So is it possible to take from the middle of that thread? No, it is not possible. But what will the second option is there? If I'll throw that rope step wise, so it is possible to take it down, means again to my hand also. So that's why first reaction is irreversible, second reaction is irreversible. So what will happen in this case? If you see the graph at equilibrium, where the cross, both the lines are crossed, so that is equilibrium point. If you add any kind of a promoter, then the reaction will go ahead, means towards the product will go, means reactant to product. If we put any kind of a reagent, which will break down again, means make it backward, so that means product to reactant again it will be formed. So that's why the work of reagent is here. Okay, so reagent is topmost means that work in this kind of a reaction. Means from equilibrium, when equilibrium touch, so neither it will go to the product side nor it will go to the reactant side. That will be a fixed point. After that, if you add the reagent, then it will make the reaction faster. Add the reagent, on the basis of that the product will be increased. If will make the slower, then it will come down. Product will convert to the reactant will be product converted to the product. Like that ammonia, when nitrogen plus oxygen and nitrogen plus hydrogen will added, it will give the ammonia. And at the point of that Lee-Chatterton principle is telling, so ammonia will again convert back nitrogen to hydrogen to nitrogen. So that is the reversible reactions. So in this case, you have to understand the things. Okay, then differential methods. So in the differential methods, so initial rate methods. Okay, so now the time is going to over. So I have actually that if we start the initial methods, and there are lots of graphs are there, so we have to discuss over that graphs. So that's why today I have to stop the class right now. 6:50 is going to be. Okay.
Yes, sir.
Okay, thank you very much. So let's complete this one, and go with your, actually so many students are asking me about that, what is that regarding your submission of your assignment. Actually, it is my advice that it is all India class. So throughout all over India, the students are joining, and you are enrolled with different study centers. So consult with your study center for the better idea. So I cannot say that which that study center, or that when they have to put your means assignment or all things. So better to consult with your study center. All if you know your study center or not.
Yes, sir.
Okay, so consult for the submission of your assignment and all the things. You should consult with your study center. It is better. Actually, I don't know that which study center is providing the assignment when and when. But after this completion of this, actually, assignment are uploaded on IGNO site for January. Yes, absolutely. It is uploaded means. Thank you, Alexander. So Alexander, so that is the thing that if it is uploaded, so you just take it, print and do it as per the instructions given by the IGNO site. So as one student say that they are telling that that assignment already uploaded in the IGNO website. So visit that website and check it out for your assignment. If any doubt, I can help you, but you just do your own work. Okay, thank you very much. So hope for the best. So we'll see you tomorrow. Thank you very much.
Hello.